Oh, good afternoon, everyone. I want to welcome you to another statistical consulting class. Of course, what I have for you today and Friday are actually called more consulting cases. I'm going to walk you through an herbicide study and also to walk you through a boss study. Of course, we all know that more consulting is usually a kind of a professional practice where our students, researchers, for the purpose of training, they simulate what I'm actually going to call real world consulting engagement, okay, in order to solve statistical problem of the client because the client, they're seeking for statistical solution. And that is why um, they actually seeking your why they consult in the first place. So this is just going to be an example of what could be maybe the research problem that the client is trying to seek a statistical solution for. And let me also say this: the essence of mock consulting, is to actually expose students, to to consulting, what I'm going to call consulting experience. Okay. Um, because at the end of the day, there's going to be a kind of feedback, okay, on whether the students able to excel or if there's any area of improvement, okay, in the consulting role. And what is fundamental here is we actually want to bridge a gap, what I call a gap between theory and application. So if we can simulate that kind of real world consulting engagement, there's a lot to learn. There's a lot to improve upon. So in the process, like I said, the communication skill of the participant will actually be improved upon. Okay. And so on like that on how to report a study analysis from studies. There's a lot of benefit, doing mock consulting. Now I'm going to go into this and in the mock consulting, like I said, the participant, they are in an acting role, they are acting. Okay, one acting as a client and the other one acting as a consultant. And at the end of the day, of course, the one that acts as a client will bring in what I call statistical problems, seeking statistical solution. And it is expected that, you know, the statistician come out with some kind of recommendation, okay? The recommendation, that's actually going to address the statistical problem in the first place. Okay, so like I said, I want to talk about, let's assume that uh, we're having a research, we are researching on this, okay, on type of, we actually want to see how um, weed can benefit from a new herbicide. Okay, there is a new herbicide being introduced, and there is a conventional product in the market that's already doing the job of weed reduction. Everybody knows in agriculture, weed is an issue. Do you hear that? Do you hear that? Weed happens to be an issue. And of course, the farmers will be looking for a way to drastically reduce weed. So if you take a look at in the herbicide study, the researchers want to show that their company new herbicide is better than a competitor product. Of course, statistics very essential because we have a way to investigate the effectiveness of what is being introduced and how we can compare that with competitor. We have statistical technique to handle that. So when you take a look at what I have right now, okay, the new herbicide are actually targeting two type of weeds. Okay, and the two type of weeds are what I display. Somebody that is coming to me to discuss, maybe to actually somebody that have this particular project after listening to the researcher, I want to see picture. I really want to understand what he's talking about. Okay, when I see this kind of picture, I'll be able to have a sense of the type of weeds. Okay, they want to try the new herbicide on. So we got Bermuda grass and mugwort. Okay, now maybe you can be visited. Okay, maybe you can be visited, and the intention of the researcher is to test their new herbicide products. They want to compare that with the conventional that we call the Roundup products already existing in the market, and they want to try that on two type of weeds. And the intention is to probably see whether the new herbicide can drastically lead to weed reduction. And of course, I am showing you the picture. Now, part of the information provided here is that the Bermuda grass is weaker. The two the two type of weeds, okay, they are not the same, putting into consideration resistance to herbicide. Now we have this information that the Bermuda grass is weaker and less resistant to herbicide than the mugwort. Okay, that information is very, very crucial. Now, whenever a client, okay, or paid a visit, I actually believe that depending on what they want, I know some of them, they haven't done anything at all. Some of them may need your help right from how do we design the study to data collection up to the analysis and up to interpretation and so on like that. Okay, so some of them they are at different stages of their research before visiting, but here we are assuming that you also want to help with the design. Okay, now I'm giving you the study design right now where we have plot A and plot B. You divide the plot into 10 by 10 grid. If you take a look at plot A right now, as you can see, it's 10 by 10, right? Yeah. And this one. Now, after doing that, we choose the first weed, okay, that came across each squared. Then for weed in plot A, apply the new homicide. For weed in plot B, apply Roundup. If we go by way of this, okay, we're like we're more intentional, like, okay, on this apply that, on that apply that. And the question is the client testing causation or association? Actually, the client is interested in testing causation, not just relationship. Causation in the sense that he actually want to isolate the effect of the new herbicide, okay, on how it can drastically reduce weight. So that is like effect of the new herbicide on weight reduction. Does that make sense? And that is the reason why it's causation, it's not an association. So the moment it is causation, then a lot has to be done. Going by what we said in the study design, that apply weed in plot A, okay? Sorry, for the weed in plot A, apply the new herbicide, and for the weed in plot B, apply the Roundup, okay? We need to follow the principle of experimental design, because whenever causation, whenever you are seeking what I call explanatory goal, this is an explanatory goal, okay? You actually want to explain causality. Definitely, if you want to do that, you need to be able to perform what I call experimental study, which in experimental study, the principle of experimental design will take a center stage. That principle will enable you to eliminate systematic biases, and which will mean that the two herbicides need to be in identical condition. Now, if I want to compare two different herbicides and they are not they are not being applied in identical condition, there's going to be an issue. There's no way I'll be able to isolate the effects of the new treatment that I talk about. Okay, now I said, what could produce systematic bias, or what may give one herbicide unfair advantage over the other? We don't want a situation whereby a particular herbicide will have an advantage over the other. Situation where that happen, then we may not be able to isolate effects of the new herbicide, okay, on weed reduction. Okay, now I've identified, some kind of, what's cool or lead to situation where one is actually going to have undue advantage, which I'm actually going to call environmental factors. That is number one. Environmental factors. Okay. Environmental factors, when you try to apply the new herbicide in a different condition, in a different environmental condition, okay, from the where you apply the conventional, that's going to be an issue. It's going to be an issue that could induce systematic bias. And that was why I actually said here, we've put into consideration from the background information that we got the other time. They said the distribution of the two type of weed, one plot has more mugwort, the more resilient weed than the other plot. We were told initially this by the clients. Okay, one of the type of weed that we want to apply this to is less resistance to herbicide. Okay, now because of that, we're actually going to refer to uh, the other potential difference that could have between the plot A and B could be soil condition. Now, before I can use plot A and B, the two of them, do they have the same soil condition? Do they have the same humidity? Do they have the same sunlight? Do they have the same density of vegetation and so on? If they do not have the same soil condition, if they do not have the same humidity, if they do not have the same climatic condition, then that could cause an interference in the relationship. You may not be able to isolate the effects of the new herbicide, which is the environmental factors that need to be controlled. Does that make sense? Now, another factor is the way the plots are managed. If they are managed differently, because even though we know the plot may not be exactly managed the same way, but there shouldn't be a significant difference between the way they are managed, because that very difference could influence the outcome. We don't want a particular aiding factor that we did not consider that could actually influence the outcome. Is there any question on that? Now, another thing I'm going to talk about is difference in application techniques. Okay, the difference in application techniques. You have to use the same application techniques. How do you apply the herbicide and the conventional one to the weed that we have, to the plots that have the weed matters. Okay, if they have different, what I call application technique, the difference in application techniques, there's going to be an issue, and that's what I'm trying to say here. So in the spraying, okay, in the spraying, I said, did they use the same way to spray the weed? It has to be the same way. That is the kind of question you're going to be asking the clients, because the client just some of them collect data and they don't really put into consideration all of these, and that could affect result. Because imagine they bring you data and you just analyze the data without asking a lot of questions. There's possibility recommendation, okay, the recommendation from your analysis may not see the light of the day, and it's going to look as if the consultant, we don't know what we're doing. Okay. So I said, was the product usage guidelines follow for both herbicide? Because if you follow, whenever a product is made, there's going to be a guideline for usage, right? If you follow it properly, adequately for one, and you did not follow it for the other, that could potentially influence the outcome. We're trying as much as possible to actually address, a potential factor, that could influence the outcome. Okay, was the person spraying the new herbicide unconsciously spraying more because he wanted to show the product was superior? I have to, if I'm going to be spraying, it has to be in the same volume. Okay, I'm not going to spray more of this and spray less of this because I actually want this to be effect of this to be significant. That's not fair at all. Okay, the way we're going to spray have to be the same. Okay, now that is we're still on the application, techniques, that the application techniques have to be the same. The difference in that could potentially impacts the outcome. Now, inspecting, did they use the same standard to determine if a weed was dead? Because a farmer know how to classify Because a weed reduction, when you talk about weed reduction, eliminating weed, you're actually going to be talking about the death rate. You believe that the herbicide is going to lead to more death rates, and you actually need to be able to have a criteria to be able to classify particular weed to be dead. Okay, it has to, you have to use the same criteria. Now, did sufficient time pass between spraying and inspecting? Because I know when you spray, it may not going to be immediately, right? You spray the weed. The weed is not going to die immediately. I know there's going to be a time, okay, that you're going to wait. Okay. Now, the same time when I spray the new herbicide and I spray the conventional one I call Roundup, okay, now I have to wait the same time for the two. Does that make sense? And that's exactly what I mean here. Okay. Okay. So, I think I've in if you did not address that, if you don't put that into consideration, okay, then there's going to be an issue, okay, and that very an issue that's going to be created is what is going to be called systematic bias. So systematic bias would definitely give the new herbicide undue advantage. Okay, it's going to give the new habitat on the, just like so some athletes, they want to run a race, okay, and for you to be fair, we are believing that we are subjecting them to the same condition. So that's because if one has unfair advantage over the other, if one athlete has unfair advantage over the other, and that very athlete actually come first or maybe record the highest the lowest time, okay, that is not going to be binding. That is not going to stand a test of time. That's not real. Okay, so the potential solutions in case this happen, I want to believe if the fundamental principle of experimental design have been followed, before in this class, I walk you through the principle of experimental design, like blocking, randomization, okay, blinding, replication, and so on like that. That has to be followed. And I'm discussing randomization here as a potential way out. Okay, randomly assign each square to the products. We're not just saying that, okay, let herbicide go to to this. No, we're not gonna do that. We're gonna randomly do that. Okay, that was why I said randomly assign the e squared in the plot to the product. When I say product, it could be herbicide, the new herbicide, okay, and or the conventional random, right, random. Use identical bottle for the two herbicide. It has to be identical bottle so that sprayer would not know which product he has. If you do that, then that's a blinding, okay, blinding, because is the sprayer know the one, if the sprayer know that, oh, this guy, oh, give me 1 second. Imagine a sprayer using this. That's not good. Maybe this one for herbicide and this one for the conventional, then we have an undue advantage here. Okay. So, and the sprayer must not even, you have to use the same bottle. The sprayer must not even know which one is for the new herbicide, which one is for the other one. Does that make sense? And that's what we call blinding. So randomization and blinding, these are, they belong to the principle of experimental design. Okay, now, that's what I said. Did the researcher follow the principle of experimental design? Okay, the moment you follow the principle of experimental design that we've discussed before, from randomization to the use of control, There's going to be a control here. The conventional is control. The new herbicide is the treatment. And then replication, blinding, blocking. Okay. Is there any question before I start showing you potential analysis of data? Is there any question? Okay, now in the data analysis here, I said, let's assume that the two herbicides are tested under identical condition. You can see that assumption. They have been, we are assuming now, they've been tested under identical condition. Okay, in other words, we have randomly assigned the square to the two treatment. Okay, now, and how do we analyze the data? Let me tell you this. Don't be rushed. Don't rush to analyze data set without understanding some basic fundamentals on how they collect the data. The way data are collected matter. I'm going to say that again. It's not just about analysis. If I analyze any data set, I'm going to get a result. That's no problem. But what really matter is actually the way the data are collected. Okay? Now, we want to assume that let's assume that we have this data set now. And you know what we're considering? We consider the numbers of weed that died. Okay? And definitely using the two treatment, that are the herbicide of the conventional. I know some weed will still survive. Some weed which is so stubborn, they will still survive. And if we want to apply statistical methodology here, you know what this guy is trying to say, okay? Um, you know, if you take a look at the totality of the weight here, okay, it's 100 for the new herbicide, 100 for the Roundup, and how many that 40 out of 100 we died using the new herbicide, and only 25 died using the Roundup. Does that make sense? And I know since our interest is actually on weed reduction, we actually want a situation where with the new herbicide, the death rate will be more. The death rate of weed will be more. Does that make sense to everyone? Any question? We all good, right? Okay. Now we have this now. And if they are being uh, if the two herbicides have been tested under identical condition with the principle of with the principle of experimental design strictly followed, then we can actually, suggest statistical technique. Now, that is when we can think of using a two sample proportion test. Okay, now, which means before using a two sample proportion test, there's a lot of consideration. Okay. In the two sample proportion test, I have to make sure that the treatments have been tested or under identical condition that I've already highlighted. Now, what I'm going to do is I want to compare the death rate from the new herbicide with the death rate for the conventional. Okay. Now, if you take a look at this from based on what you've done before, right? Based on what you've done before, okay, we actually having to hypothesis under consideration. We got the norm, we got the alternative. And if you look at in the alternative, what am I trying to say? My P1 is the death rate for the weed sprayed by the new herbicide. And P2 would be the death rate for the waste spray by the runoff. And of course, you can see my alternative is greater than sign because I want to prove to the world, the company really want to prove to the world that the death rate, okay, the death rate of the weed spray by the new herbicide will be more. And that's why you got a greater than sign. Does that make sense? Now, after looking, after the assumptions satisfied, with the way the data are collected, you now need to come back now into the assumption of this two sample proportion test. The technique that you want to use has assumptions that need to be satisfied. Okay, before going into this technique, okay, we actually need to fulfill uh, the conditions that I mentioned that have to be identified with the way the treatments are tested. That has been satisfied. Now, the next now is I'm going into a two sample proportion test, which is a technique of statistics that I'm recommending. So the next thing I'm going to do now is what are the assumptions of the two sample proportion test? Because the assumptions have to be made before I can do anything. Now, there have to be two independent random samples and at least 10 successes and 10 failures in both. In the lower statistics course, lower level statistics course, I know you've come across when they're going to say N1, okay, P1. You remember that? Has to be greater or equal to 10. Do you remember stuff like that you've done before for normality? Okay, and N1, okay, into 1 minus P1. Okay, N1 into 1 minus P1, okay, has to be greater or equal to 10. This is for one population, also for the other population, it has to be like that because t-test is a parametric procedure that have assumptions. And the moment that is met, then the next thing is to set our significance level. The significance level alpha, which is the maximum probability of committing type 1 error. The significance level is what we're going to compare our p-value with to be able to take decision. Okay. Now, like I said, this is going to be a two sample proportion test. Based on the table, okay, you'll be able to find the p cap 1, okay, in the formula, the p cap 1 is actually x1 divided by n1, which is going to be n1 will be the numbers of weed sprayed with new herbicide. X1 will be the number of deaths, okay, and that's what you have here, which is going to be 40 for this one over 100. For the conventional product is 25 over 100. And that is exactly, and of course, the sample size. Okay, the sample size in both cases. Okay. Now, some of you you may be wondering what is going on here. Okay. Um, what is it? What is this guy called? Give me 1 second. Take a look at this pickup. How do they get a pickup, which is a combined proportion? The combined proportion, if I really want to get that, if I really want to get the combined proportion, it's actually going to be the number of successes, okay? The number of successes with the herbicide plus the number of successes with a conventional, which is the write-up, divided by the totality of the sample. That will be N1 plus N2. And of course, N1 is 100, N2 is 100, and that's why you have this guy here. So the number of success here is the death rate, okay? The number of death. Okay, do you understand the pickup now? Then at the end of the day, you have this particular value, okay? And that particular value is greater than the critical value. Or if you get a p-value associated with that, it's going to be 0.012, and that is less than the 0.05 level of significance. And if that is less than, it means you are going to reject the non-hypothesis, right? So rejecting the non-hypothesis, it means the new herbicide has actually led to a drastic reduction in the weed. Okay, that's exactly what we mean. Is there any question on this? Is there any question? We're using the idea of a normal distribution here, and that's call for the reason why you need to investigate whether the number of successes is at least 10. Don't forget that. And that was why I said we have statistically significant evidence that weeds sprayed by the new herbicide are more likely to die than weeds sprayed by the Roundup. Now, another question is, how do you mean by the statistically significant evidence? Statistically significant evidence just because the p-value, that we obtain is less than the given level of significance. Okay. Now, when uh, what I've done here, what I've done manually here, I can also do that in out. Okay. This is just telling you how to do that in out. You can see alternative. I indicated greater. I indicate the greater. You can see that. And you can see my p-value here. Okay. My p-value is actually less than the level of significance. Okay. Um, there's something I need you to pay attention to. Okay. There is this one is a two sample test for equality or proportion without continuity correction. They gave that p-value. And with continuity correction, he gave that p-value. Because at times, we need to have, consider continuity correction as well. But if you take a look at the two here, where the p-values are kind of close. Now, if I don't want to go, at times, different, more than one statistical technique may be appropriate, okay, to actualize an objective. Another way we can look at that is to go by way of chi-square test. In the chi-square test a discrepancy between the observed and the expected. Now, since I have a table like that, what I have in the table, they are observed values, then I'm going to get the expected value for them. Okay. Now, what I'm actually testing with the chi-square, I'm testing whether relationship exists, association exists. Okay. The chi-square test is a test on just in a categorical analysis where you test whether there's an association between two categorical variables. Now, at the end of the day, if you take a look at the p-value associated with the test, also less than 0.05, okay? And of course, you know, so what we've done here, we're trying to say a 2x2 contingency table, the two-sided two sample proportion test is equivalent. Okay, they're going to be equivalent. But if you conduct a two, what we did the other time was a one directional t-test, right? If you do two tailed on non-directional, and the p-value that you're going to get with the chi-square and that of the non-directional, which is the two tests, is going to be the same. But the issue with the chi-square, with the t-test we conducted, we indicated a greater than, which means we can see the direction. But chi-squared, there's no direction. The chi-square is only going to tell you, oh, relationship exists. And that's why you say the chi-squared does not tell us the direction. But we have a way. Does not tell us the direction, we mean it's not going to tell us the herbicide that is more superior in killing weeds. Does that make sense? But the chi-square is only going to tell us there's an association. But let me tell you this. If I want to know the strength of association, okay, in a categorical variable, of course, that's what we can investigate what I call odd ratio, relative risk, and all of that. Okay. Okay, so how to do that now? Okay, that's how to do all of that now. Okay. Now, uh, Another way we can investigate is to go by way of logistic regression. So why is the logistic regression coming in? Because the response variable is categorical. Categorical in the sense that it's either events of death occur or not. Does that make sense? Now, as I said, the benefit of using logistic regression model is that you can also, and in addition to that, looking into the response variable we know is categorical. The logistic regression we also enable you to control other factors that could influence the outcome. Okay, so we can incorporate them as covariates in our model in a way to adjust or to control for them. Okay, and so if you take a look at what I have for herbicide, I'm going to call herbicide X. Design matrix is going to be herbicide X. And if S equal to 1, I'm referring to new product. If S equal to 0, I'm referring to random. Let me tell you this. It's not as if because I call new products 1 and random 0, that doesn't mean new product is better from the 1. No, it's just for labeling. Does that make sense? There's no any numerical advantage here. Okay. Now, the response variable, okay, is die, Y, which is categorical, okay? 1, 0. 1 when the we died, 0 when the we survived. For the, you can see for the herbicide, also categorical, 1 for the new product, 0 for the random. Now, there could be other potential factors like blocking. I told you the other time, like blocking, like other things that we know that could potentially affect. And in that regard, we're actually going to be testing. What we're going to be testing, in the logistic regression is going to be beta 1 equal to 0, beta 1 greater than 0. And of course, you're going to have a log of odd ratio. You can see that now. Okay, I'm including block, and there could be other factors in the model that have a potential that could influence the response variable. And of course, the in out, how do we handle that in out? How do we handle that in out? This is the code. Okay, this is the code, right? Family equal to binomial. But right now, you're gonna want to say Y on S, okay? Y on S, I'm only focusing on herbicide. I didn't, like in this one now, this is a simple model. I didn't include other factor, and this is what I have. I needed to pay attention to this, okay? To what I have. What I have here, the estimates here. I needed to pay attention to the estimate here. You know what the estimate is called? We call them log odd estimates. We call them, let me write. So we call them log odd estimate. Now you can see the p-value associated. What do you see? 0 point. The p-value here is also indicating significance. Okay, indicating significance, indicating that the new herbicide is statistically or significant. In fact, the beta 1 is greater than 0. You can see we have used three different approaches of the style, three different techniques in statistics now, and we are still taking the same decision. At times, more than one technique in statistics could be appropriate for a given problem. Okay, that is going to be the end of the of that herbicide study. So what I have for you on Friday is bus study. And this very bus study is very, very important because here I'm actually going to introduce you on Friday to what I call repeated measure. gonna introduce you to repeated measure of number because that is needed in this bus study. Is there any question for me before I go today? Make sure you all stay safe. Have a lovely day. Okay, before you go, if there is any one of you who doesn't, maybe you don't have a partner, like I said, I'm flexible for the mock, reach out to me. Imagine two people reach out to me. Oh, I don't have a partner. I don't have a partner, then I'm gonna match them. Does that make sense? I'm flexible. Reach out to me. Okay? Make sure you all stay safe. Have a lovely day. Bye for now, everyone.